In section 6.1, we want to discuss velocity and net change. This will include a review of motion, speed, position, acceleration, and falling bodies problems. Now, this section is about some powerful real-world implications for the concept of the integral, and it will feature some previous friends like position, velocity, acceleration, resource consumption, population growth, other things. Now, we begin with a review of definitions for one-dimensional motion. Now, in Calculus 1, we are dealing only with single dimension motion, and we are going to continue with that because we have to start simple and kind of build up from there. Now, why is motion such a big deal? Well, one, it's beginning of physics class, right? Because they usually have you begin with Newtonian mechanics. And Newton himself was, of course, developing calculus as a mathematical way to explain the things that he was trying to explain with physics, namely the three laws of motion. Objects in motion tend to stay in motion. Objects at rest tend to stay at rest. Objects going in a direction tend to keep going in that direction unless they're acted upon by another force, right? And so calculus was the math behind what he was doing. And so it's a good place to begin for us as students. Also, we all have been in motion at some point, so we have a sense of what this is like. So we talk about time when talking about motion. We always use time as our independent variable because, of course, time keeps on slipping into the future. Or is it ticking into the future? It's from the Steve Miller Band. It's an old song. Feel free to look it up on YouTube. All right, so if time is our independent variable, then position is s equals f of t of an object. Now, I don't know about you, but when I was in school, I could never figure out why they let it be s. Because it's position, shouldn't it be p? And the answer is not so fast, because Newton and Bernoulli and Euler and all the others were working in Latin. And in Latin, the word for position is situs, right? As in where our word situation comes from, right? Or if you've ever heard of a history teacher talking about in situ, right? In situ means in position, right? It's the art is sitting in its place, right? So when you go see a painting in situ, it means it's in the place where it was meant to be, right? Usually it's a bigger thing with sculpture, right? So situs is the Latin word for situation, situated, right? Positioned. So when Newton and his buddies were all, well, actually some of them his enemies, were all working, they were working in Latin. And so they picked up the Latin word for position, which is situs. So that's why it's S, in case you wanted to know. And we will stick with that. P actually gets used for other things. All right, so S is equal to F of T is how that object changes its position over time. So if you have S equals 0 right here, right? Now remember, we're only going in two directions, right? We're only going either forward and backward, up and down, because we're only dealing with one dimension at this point. When we go on to later on, we'll actually deal with two in this class, and then lots more when we get into Calculus 3. You'll be able to work on spirals and stuff like that. But for us, it's going to be, right now, either up and down or left and right, and that's it. Now, this particular object is moving left and right. So we have the position at t equals a is right here. Position at t equals b is right here. B is greater than a, right? And so we're moving this way, right? And so the difference in our position is called our displacement, right? Displacement is s of b minus s of a. Now in this case, it is greater than 0 because we moved in the right direction, right? Whereas in this case, the displacement is negative because we moved left. So this is assuming that right is positive. Sorry for all you left-handers out there. All right, right is positive and left is negative. And that's pretty common because we usually think of this, well, it's almost always that way, because this is basically the x-axis. And so this would be positive over here and this would be negative over here, right? So we usually assume that right is positive and left is negative in this direction. For up and down, we usually assume up is positive and down is negative. Okay, which is what I was making a comment of right down here, right? So this one had positive displacement, right? Notice this is positive because we moved right. And then this one is negative. That's why it's less than 0, because we moved to the left. Now, which direction is positive and which is negative is kind of arbitrary. Arbitrary meaning we make it up, right? So we usually almost always assume up is positive, right is positive. When you're going forwards and backwards, like when you're driving a car, right? So if you're driving a vehicle, forward is positive, reverse is negative, right? Going backwards. North and south, because we live in the northern hemisphere here. Sorry, anybody watching from Australia or New Zealand, but we assume north is positive, south is negative, and east and west, because east and west work on the same principle as right and left, hypothetically speaking, on a compass heading, then east, that's a typo. East is positive and west is negative. Since we're in a reviewing mood, let's also review the relationship between acceleration, velocity, and position, which of course ties into this one-dimensional motion. All right, so velocity is the rate of change of position. Here we go. Just gonna write this. In other words, rate of change, of course, is another way of saying the derivative. So velocity is the derivative of position. So position is the antiderivative of velocity. Right? You learn both of these in Calc 1. You learn that velocity is the rate of change of position, and then you learn the position is the antiderivative of velocity. And similarly, acceleration is the rate of change, aka the derivative, of velocity. Therefore, velocity is the antiderivative of acceleration. Okay, so let's think about our three functions here. We have position, we have velocity, which is not speed. It's related to speed, but it's not the same thing. Acceleration. Velocity is speed with direction. Okay, now let's think about what we just learned. We said that velocity is the derivative of position, and acceleration is the derivative of velocity. That means that I can differentiate, aka take the derivative, to move my way down. So I can go from position to velocity, because velocity is the derivative with respect to time of position. Similarly, I can go this way and say, okay, acceleration is the derivative of velocity. Right? So in Calc 1, we learned to do this, right? We start with position, we go to velocity, velocity to acceleration. And then, if we were paying attention in Calc 1, at the very end of the course, they tell you can reverse the process, right? Which is the antiderivative, aka the integral, right? Right? That's what these are saying. Okay, so that means that differentiate, aka take the derivative, is over here, but integrate is over here. And we can work our way backwards up the chain. So if I have acceleration, I can take the integral of acceleration with respect to time and get velocity. And then I could take the integral of velocity and get position, that I can work my way back up the chain. And these are constantly working together, right? So if you have this one and want that one, you have to take the derivative. If you have acceleration, you want velocity, you have to take the integral, and you can work back and forth through this web. Very important to understand this. Now, some other things to think about. We won't deal with this too much, but you will a little bit in Calculus 3. Namely that momentum is mass times velocity, and force is mass times acceleration. Force equals mass times acceleration is actually one of the formulas that my physics teacher always made us just know that. So force is mass times acceleration. Obviously, velocity and acceleration then have bigger implications for momentum and force. And that means they also have implications for work as well. Now, there's more derivatives of position included here, just in case you were interested, because I find them fun. So the derivative of acceleration is called the jerk function. The derivative of the jerk function is called the jounce, also called the snap function. And then they literally name them snap, crackle, and pop, like the cereal. So the derivative of jerk is snap, the derivative of snap is crackle, the derivative of crackle is pop. You're welcome to look up the Wikipedia article about that. And yes, those really are named that. That wasn't just made up. Okay, so there are a few other ones to know. So the rate of change of work is power. Power is the rate of change of work, because work is measured in joules, and power is joules per second. So this would be in joules, aka Newton meters, and power is in joules per second. And that means that work is the antiderivative of power. Another one that we will work with actually quite a bit is flow. So flow is the rate of change of volume. Think about it. If you have a bathtub full of water, the rate of change of the volume of that water as it flows in or flows out is your flow rate. And then this would be volume, would be the antiderivative of flow. And then just another one for fun, which hopefully you learned at some point, which is the marginal cost. Very important for economics, actually. All right, so the marginal cost, the cost to make the next item is the marginal cost. It's the rate of change of cost. So it's like dollars per item, if you want to know that. And then this would be cost is the antiderivative of marginal cost. Marginal cost is C prime, right? Oh, and just in case you were interested in units, so this one would be dollars per item, and this is dollars, right? So dollars per item. That's how that goes. Flow is cubic volume. So volume, it depends on how you do your volume. If you do it in meters cubed, say, right, just pretend. Volume could be a lot of things. Centimeters cubed, meters cubed. It could be gallons if you're working in the imperial system, the English system. So this would be meters cubed per minute, say, or something like that. Or meters cubed per second, depending on how you do it. With volume in particular, we have a lot of ways we could do this. Gallons per minute, gallons per second. There's lots of ways we could go with that.